Welcome to Lecture 6.4, Solving PDEs with Fourier Transforms. This is the natural follow-up to the previous lecture, which was about solving PDEs with Laplace transforms. Though these are similar, one of the main differences is that Laplace transforms act on the variable t, and Fourier transforms act on the spatial variable x. Let's first recall what the Fourier transform is. This is a linear operator that inputs a function of x, space, and it outputs a function of frequency, f of omega. And there are multiple ways to define it depending on what constant you want to put in front and a few other slight modifications. It doesn't really matter, they all have their pros and cons, but the one that we are using is defined as follows. So the Fourier transform of f is a function f hat of omega, which is the integral from negative infinity to infinity of f of x times e to the negative I omega x dx. I should say that if you have not watched my prior lecture on Fourier transforms, please do that first. Of course, the Fourier transform is not going to be defined on a whole bunch of functions because this integral need not converge. However, there is a very nice collection of functions for which the Fourier transform is not only defined, but has some very nice properties. And we'll denote this by S. So let S be the subspace of C infinity of R. So these are the infinitely differentiable real-valued functions that moreover have continuous derivatives. So sometimes these are called the smooth functions. So S is the subspace of these, consisting of, here's how you should think of this, the functions that decay as x goes to infinity faster than any polynomial. So formally, S is a set of smooth functions such that the magnitude of the derivative is less than or equal to, asymptotically, a constant times the nth, or the negative nth power of x as x goes to infinity for all k and for all n. So that's a mouthful. Really what you should take from this is that the decay faster than any polynomial. So let me draw a quick picture. So let's take the polynomial 1 over x. So 1 over x is going to decay like this. 1 over x squared is going to decay faster. So this is 1 over x squared. 1 over x cubed is 1 over x to the fourth. All these are going to decay fast, but what's something that's going to decay faster than this? Well, what about f of x equals e to the minus x? This is something that is going to decay faster than any of these things. The space S is called the Schwartz class of functions, and it turns out that a function f is in S if and only if its Fourier transform is in F. In other words, the Fourier transform is a linear operator on the space of Schwartz functions. So if you input anything in here, you get back something in here, and it's actually more than that. It's not only a linear operator, but it is what we call an automorphism. It preserves structure, and there's a lot of theory behind that we won't even get into. It's well beyond the scope of the class. But what you should know is that if you take a function f of x in here and you apply the Fourier transform, you're never going to get outside of there. In particular, the Schwartz class is a bijection between the subspace S and itself. The last thing that I want to tell you about the Fourier transform of a single variable function is the convolution theorem. Now hopefully you joined us from my previous lecture on Laplace transforms where you saw very similar results about those. So before I get started, let me remind you what the convolution of two functions is, if you don't remember. So f star g, so if these are two functions of a single variable, it might be t, might be x, it doesn't matter. This is the integral from 0 to t of f of t g of u minus t dt. So if you want some explanation as to what this means in terms of the graph and some intuition behind this, go back and watch the previous lecture. But one reason why we are interested in this is because, of course, Fourier transform is linear. So the Fourier transform of AF plus BG is A times the Fourier transform of F bar, or F hat, plus B times G hat. So sums break apart, constants pull out, but the Fourier transform of f of x times g of x, unfortunately, but not surprising, is not equal to any nice formula, because integrals have this linearity property. They do not have a multiplicative property. However, fortunately, convolution comes to the rescue. It almost looks like the multiplicative property holds here, except you need a little asterisk. So this says that the Fourier transform of the convolution of f and g, not quite the product, but something close, is equal to the product of the Fourier transforms of f and g. If you take the inverse Fourier transform of both sides, it will follow that the convolution of f and g is the inverse Fourier transform of the product of the Fourier transforms. Saying it like that doesn't make it sound very useful or impressive, but let me motivate it a different way. Suppose you are in the frequency domain and you need to invert, so you have something that you need to compute the inverse Fourier transform of. And unfortunately, what you don't have is something that you can find in the table very easily, but you have the product of two things that you know how to invert individually. So you have f hat and g hat. Well, if you take the inverse Fourier transform of those, you get f and g, take the convolution, there you go. That's the inverse Fourier transform that we seek. Now there are some basic properties of convolution. I should mention that I went over in the previous lecture. Again, I encourage you to not only look at the previous lecture, but look at one way back in my section 3. I was all about Fourier transforms. So things like the convolution of f and g equals the convolution of g and f. So that's one thing that is not at all obvious if you look at the integral definition, but it certainly, perhaps surprisingly, does hold. Let's move on to the Fourier transform of a multivariate function. The basic idea is the same as what we saw with Laplace transforms. We treat the second variable as a constant, and it just goes along for the ride. So given a function u of two variables, x and t, define its Fourier transform as follows. So f applied to u is a function u hat of the variables omega and t, and that's the integral over the whole real line of u times e to the negative I omega x dx. So we are integrating out x, and we are ending up with an omega. So that's why our function u hat is of omega and of t. Much like the Laplace transform, the Fourier transform turns x derivatives into multiplication, but it leaves t derivatives unchanged. Remember, the Laplace transform was on the time variable. That changed t derivatives into multiplication by s, and it left x derivatives unchanged. So to verify this, I'm going to actually go back to a single variable function. And just know that when you add t and it goes along for the ride, that's not going to change any of this. So let's suppose that we have a function f of x, and its Fourier transform is f hat of x, and we wish to figure out what is the Fourier transform of the derivative. So to do that, the Fourier transform of f prime, by definition, is the integral from negative infinity to infinity of f prime of x times e to the minus I omega x dx. So we can integrate by parts. We can let u be equal to, see, which one do I want to do? Let u be equal to the exponential e to the negative I omega x. So du equals negative I omega e to the negative I omega x dx. And then dv equals f prime of x dx. So v equals f of x. Notice I specifically chose the function f because I knew I was going to do u substitution, and I didn't want to have u substitution along with a function called u both. Okay, so now this integral, I'll move down here, it's u times v, so it's that's f of x e to the minus I omega x from negative infinity to infinity minus v du. So minus the integral from negative infinity to infinity of v du. So that is negative I omega f of x e to the minus I omega x dx. Now, one thing that we need for Fourier transforms, I'm sure I mentioned this in my original lecture, is that the function f must be absolutely integrable, which means that take the absolute value of f, it must have finite area under the curve. So if that's the case, then it has to be true that the limit as x goes to plus or minus infinity of f of x is equal to 0. So that means that this limit here, when you plug in infinity, or you take the limit, that this thing here has to go to 0. So now what we get is, well, we have minus, we can make that a plus, we can pull out the I omega as a constant, and we get I omega times the integral from negative infinity to infinity of f of x e to the negative I omega x dx. That you should recognize as the Fourier transform. So the Fourier transform of the derivative is just I omega times the Fourier transform of x. So the Fourier transform turns x derivatives into multiplication by I times omega, and it leaves t derivatives unchanged. Thus, for a two-variable function, the Fourier transform of the x derivative of u is I times omega times the Fourier transform of u. The Fourier transform of the second x derivative of u is the square of I omega times the Fourier transform of u. So of course that's negative omega squared. And in general, every time you take a derivative, you get out another factor of I times omega. Finally, the Fourier transform of the first time derivative of u is just the time derivative of the Fourier transform of u. A lot like Laplace transforms, just switch the role of x and t, and it's a little bit different. Here there's no initial value that you have to subtract off like there was for Laplace transforms. Also not surprising is that the convolution theorem carries over to multivariate functions because the t goes along for a ride. So for functions f and g of x and t, the Fourier transform of their convolution is the product of the Fourier transforms. And if you take the inverse Fourier transform of both sides, you get the following situation. Anytime you have the product of two functions in omega and t that you need to invert, take the inverse Fourier transform of, if you can invert them separately to get f and g, then do that and take the convolution and you'll get what you need. Let's start with an example of computing the Fourier transform of a Gaussian function. Particularly, let's do this Gaussian function, u of x equals e to the negative ax squared, where a is some positive constant. So this is in the shape of a bell curve. Of course, we can't guarantee that this is going to have area 1 underneath it because we don't have any idea what a is, but we could scale this to make it an actual normal distribution if we wanted to. I did some examples of Fourier transforms in an earlier lecture in section 3 when we introduced them, but I particularly want to do this one because these Gaussians occur, or they arise when we solve PDEs on infinite domains. And that shouldn't be a surprise. Earlier in this section, when we solved PDEs on unbounded domains with other methods, we saw Gaussians arise. And so they will arise in our last two examples. Okay, so let's begin by just using the definition. The Fourier transform u hat of omega is the integral from negative infinity to infinity of e to the negative ax squared times e to the negative I omega x dx. So this, of course, is an integral in x. So the derivative of u hat with respect to omega, key point here, with respect to omega, has nothing to do with x. So it's tempting to use the fundamental theorem of calculus, but remember, it's a different variable. So this is the integral. We can bring the derivative inside. So it's the integral over the real line of e to the negative ax squared times d omega of e to the negative I omega x dx. So, of course, the derivative of this exponential function, we pull out the constants. I, negative I times x comes out. So we get negative I comes out in front times the integral over the real line times x e to the negative ax squared e to the negative I omega x dx. Okay, now this piece right here, this x times e to the negative ax squared, that should remind you of the derivative, using the chain rule of e to the negative ax squared. It's not quite because there's constants. So let's check. So what is the derivative, d dx, of e to the negative ax squared? Of course, that is, by the chain rule, it's negative 2ax e to the negative ax squared. So that's what we have here boxed, except there's a negative 2a in front. Well, actually, we already have the negative sign here. So what we don't have is the 2a. So what I've written down here is, so what we have to do is so the thing in the box, we can replace it with this if we divide by negative 2a. So there's a negative sign that will cancel with this one. So what we get is I over 2a times the integral over the real line of the derivative of e to the negative ax squared times e to the, let's put parentheses here, e to the negative I omega x dx. Now let me box this so you can tell. I should box that, and I should probably box this as well, and then there's a negative sign that we lost in here. I think you get the idea. Okay, so what have we just done? Well, actually, I should say, what do we have here? This should be familiar. This is the Fourier transform of this thing in the box. And what is that thing in the box? That's the derivative of u. So this is I over 2a times the Fourier transform of u prime of x. So again, the Fourier transform of a function is that function times e to the negative I omega x integrated. And that function is u prime. Next, remember what the Fourier transform of the derivative is? It's just the Fourier transform of the function times I omega. So this is I over 2a times I omega times u hat. So let's summarize what we have. We have the derivative of the Fourier transform of u, which is what we're trying to find the actual Fourier transform, but we know the derivative is equal to the Fourier transform itself times omega over 2a times negative 1. So let me write that out. The derivative of u hat is negative omega over 2a times u hat. We're trying to figure out what u hat is. And now we have a differential equation in u hat. This is something that we know how to solve. So let's do it. So this is d u hat over d omega equals negative omega over 2a times u hat. How do we solve this? Be careful, that's not a constant this time. We can't just take an exponential function. We have to separate variables. Tricky, right? So d u hat divided by u hat equals negative 1 over 2a omega d omega. We can integrate both sides. The left-hand side becomes the natural log of the absolute value of u hat. The right-hand side is, let's see, this is going to be omega squared over 2, so this will be negative 1 over 4a times omega squared plus a constant c. If we exponentiate both sides, then the left-hand side becomes u hat of omega. Just remind you it's a function of omega. And the right-hand side, we can bring this c down, and we get c, we'll re-Christian it, c e to the negative omega squared over 4a. Now, normally this would be a positive constant, but we can make it positive or minus and drop the absolute values signs here. So this is our answer. This is the Fourier transform of u. It is a constant times e to the negative omega squared divided by 4a. Well, it's not quite good enough because what's our constant? This, unlike differential equations, we need a single answer here, not just an infinite family. That's not going to do. So we have to figure out what the constant is. So let's find c. So to do that, let's plug in 0 for omega. So u hat of 0. Oh, and let's remind ourselves what this is. Remember what the Fourier transform is? U hat of omega is this integral, so u hat of 0 is what we get when we plug in 0 for omega. So u hat of 0 is, by definition, the integral over the real line of e to the minus a x squared times 1 times dx, and it's something you may remember how to integrate from vector calculus. This has no indefinite integral, but there's a neat little trick to make it a double integral and integrate over the plane. You change it into polar coordinates and you get a, remember r d theta, you get an x that pulls out. I'm not going to go over that in this class, it's a little bit beyond the point, but this, it's not too hard to show using a double integral that the value of this definite integral is the square root of pi over a. So notice from here that u hat of 0 is clearly equal to c, because the exponential becomes 1, and so that tells us that c is equal to the square root of pi over a. So now we have our final answer. We have the Fourier transform, u of omega, is the square root of pi over a times e to the minus omega squared over 4a. Remember that. Let's put it in our back pocket because it's going to come up fairly soon. Next, we'll use the Fourier transform to solve an ODE. This is a very simple one. U double prime equals U. So you should look at this and think exponentials or cinches and Cauchys. But now we're going to have a forcing term, f of x. And f is going to be in the Schwartz class. That's probably stronger of a requirement than we need, but we'll reevaluate it at the end of this problem. So remember, that just means that f dies out faster than the inverse of any polynomial. Now, when you look at this, you should be thinking, or at least what I think anyways, is, well, what about solving it by solving the homogeneous version equation first, UH of x plus any particular solution? Now, that's what I would do. If we did that, we would get C1 e to the x plus C2 e to the negative x, or you can use cinches and Cauchys, plus any particular solution. And that's great if you can find a particular solution. But what we're going to do now is just take a general function where maybe if this is some sort of bell curve, we know how to compute its Fourier transform, but other than that, we don't know how to solve or how to find a particular solution. Okay, let's get started. The first thing that we always do is we take the Fourier transform of both sides. And if we do that, we get Fourier transform of u double prime equals the Fourier transform of u plus the Fourier transform of f. So this is I omega squared times u hat equals u hat plus f hat. So of course I squared is -1. So let's see, we can move u over to here and f over there, combine terms, and what do we get? We get 1 plus omega squared times u hat equals f. All right, not f equals negative f hat. Does that look right to you? I think so. Yeah, so now we can solve for u hat, and we get that u hat equals negative 1 over 1 plus omega squared times f hat. So looking at this, this is where we want to apply the convolution theorem. We have two functions. This is f hat of omega, and we know that the inverse Fourier transform of that is going to be just f, and then the inverse Fourier transform of 1 over 1 plus omega squared, that's something that we can either compute directly or look up using a table. And I'll just tell you that the Fourier transform of 1/2 times e to the negative absolute value of x, that this is indeed equal to 1 over 1 plus omega squared. And that's something I'll probably put as a homework exercise. So this function here, 1/2 e to the negative absolute value of x, that looks like something like that. Okay, so by the convolution theorem, if we apply the inverse Fourier transform to both sides, so let me say f inverse and convolution, then we get that u of x equals negative 1/2 e to the negative absolute value of x, that star, so the convolution of that with f of x, the inverse Fourier transform of f hat. So this is, by definition, negative 1/2 times the integral over the real line. Now let me see, I don't want to use u as my dummy variable, because I've done that. So let me use y as my dummy variable. So, and again, the order of this does not matter. So you can say it's e to the negative x minus y, or negative absolute value of x minus y, times f of y dy. And of course you could switch the order of these, because order does not matter, and get negative 1/2 times the integral of e to the negative absolute value of x times f of y minus x dy. That would work as well, depending on how complicated f is as a function. Before we move on to the final example involving an actual PDE, I want to say a couple of words about this solution, several different ways to write it, to the ODE. Perhaps it was a bit surprising because maybe you were expecting that the solution would be a two-dimensional affine space, right? Because I've been hitting that hammer all class. C1 and C2 are your 2 degrees of freedom. And in general, it is the case that a second order ODE will have, linear ODE will have a two-dimensional affine space as a solution. However, when we add initial conditions or boundary conditions, we generally get rid of those, or we place restrictions on what those coefficients are. And we don't have that here because we have an unbounded domain, but what we do have are implicit restrictions on the limit as x goes to plus or minus infinity on u of x and f of x. These things have to be 0. We saw this in the previous lecture. I think we had a restriction that u of xt was bounded when we solved the PDE, and then we took the Laplace transform. I think we had something like u of x s equals a of s e to the negative root s x plus b of s e to the positive root s times x. Something like this. And the fact that it was bounded told us right away that this exponential couldn't be there because that would blow up. So similarly, we have multiple restrictions on the function, and so that is going to basically do the same effect as initial conditions or boundary conditions would and get rid of those constants. And so that's why this solution that we get doesn't have any constants in it. It's just a single function. Now, as promised in the beginning of this problem, I want to return to the assumption that f is in the Schwartz class. So looking back at this, I don't think we actually need that restriction. I think we can relax it. We basically just need that the Fourier transform of f exists and this integral exists as well. If those happen, then we're good. And I'm pretty sure, don't hold me on this because I'm really not an expert on exactly what functions we can do things like this for, but I'm pretty sure that if this function is continuous and bounded on the entire real line, then I think all of this will carry through. Finally, we get to our original goal of using the Fourier transform to solve a PDE. We will apply it to the following Cauchy problem for the heat equation, where the initial condition is a function f of x, and for now we'll assume it's in the Schwartz class, though as before I'm pretty sure we can relax this to be any continuous bounded function on the real line, but just for now let's just assume it's in the Schwartz class. So here's our PDE, ut equals c squared uxx. Let's start, as we always do, by applying the Fourier transform to both sides. So the Fourier transform of ut equals the Fourier transform of c squared uxx, and let's now apply it to the initial condition as well. So the Fourier transform of u of x0 equals the Fourier transform of f. So this here, remember, is the t derivative of u hat equals c squared times I omega squared times u hat. So the two derivatives turn into multiplication by I omega. So we get u hat t equals negative c squared omega squared u hat. Okay, let me box that. That is an ODE. We turned the x derivatives into multiplication, so now we have one variable instead of two. Before we solve that, let me reduce this a little bit. So this is u hat of omega 0 equals f hat, and that is of omega. Okay, so now back to our ODE. This is just exponential decay. So just to remind you, this is just like y prime equals negative c squared omega squared y. You could solve that, right? It's just an exponential function. And that's what we have here. It just looks a little more intimidating. Okay, let's remind ourselves, before moving on, that u hat is a function of omega and t. The omega just goes along for the ride because this is a differential equation in t. Okay, so u hat of omega t, again following this as a guide, is I'm going to use the constant a because I have a c right here already. So a times e to the negative c squared omega squared t. So this is our general solution. And now to figure out what a is, we have to use our initial condition. So let's plug in t equals 0. So u hat of omega 0. If we plug in t equals 0, we get a. So we go back to our initial condition, and the Laplace transform of that tells us that u hat of omega 0 equals f hat. So we get a equals, let me do this in black, a equals f hat of omega, and that's from our initial condition. So that tells us what a is. Now we have our particular solution, u hat of omega t, well, it's the Fourier transform of the particular solution, which is f hat of omega times e to the negative c squared omega squared t. Or if you want, you can write it in the opposite order, e to the negative c squared omega squared t times f hat of omega. Okay, so two different ways to write it. Now all we have to do is figure out how to take the inverse Fourier transform of this. I don't think I've been saying Laplace, but I might have let it slip earlier. So if I say Laplace, I mean Fourier. Now the reason why I've written it in this way is because we're going to use the convolution theorem. Here we have two functions, f hat and this exponential, and we want to compute the inverse Fourier transform of their product. So we have to compute the inverse Fourier transform of them individually and then take the convolution. Let me remind you what that says. So the convolution f, or of f and g, is the inverse Fourier transform of f hat. I'm not going to put the variables, f hat times g hat. I'll leave it like that. It's simpler. So now we just have to figure out how to compute the inverse Fourier transform of f hat and of this exponential. And f hat is easy. Inverse Fourier transform of that is just f, by definition. So what about the exponential? Well, think back to example 1 in this lecture. We determined that computed that the Fourier transform of a Gaussian e to the negative a x squared was the square root of pi over a times e to the negative omega squared over 4a. I told you that would come back. So let's highlight that. And now look at what we have here. So in the frequency domain, we know how to go backwards from this. And the frequency domain over here, this is close to that, but not quite. So I claim that if we let a take the place of, or if we replace a with 1 over 4 c squared t, I think that's right. So if we divide, so if we take omega squared divided by 4 times this fraction, then the bottom of that will come out on the top, and we will get, let me write that down, e to the negative omega squared divided by 4 over 4 c squared t. The 4's will cancel, and we will get e to the negative c squared omega squared t, and that's exactly what we have here. Now I left some space because we have this square root as well. Although actually I don't need to put the square root here. So if I take f of, put a parentheses here, e to the negative a x squared, where a is this, then I get this exponential times, yeah, so the square root would go here, but I don't want that there, so I need to divide, so I need to divide by that square root, so I need to put root a divided by pi in front of here. So f, Fourier transform of root a over pi times e to the negative a x squared, where, once again, a is equal to 1 over 4 c squared t. That will get me, as desired, e to the negative c squared omega squared t. So to summarize this, we just found that the Fourier transform of, let's see, what is the square root? So this is the square root of 4 c squared t times pi. So this is the, let's write it as 1 over the square root of 4 c squared pi t times e to the negative ax squared. So that's negative x squared divided by 4 c squared t. That will give me e to the negative c squared omega squared t. Funny, the hardest part about this is the algebra and dividing by these fractions and the variable substitution. Okay, so the inverse Fourier transform of this guy right here is this sucker. So now we can apply the convolution theorem, and we get that u of x t. So let's apply inverse Fourier and convolution. And we get that it is, well, it's the convolution of f of x with this guy, so with 1 over root 4 c squared pi t times e to the minus x squared divided by 4 c squared t. And by definition, that is the integral from negative infinity to infinity of 1 over, I could have pulled that out if I wanted to, 4 c squared pi t times e to the, and again I'm not going to use u as my dummy variable, negative x minus y squared, divided by 4 c squared t times f of y dy. And of course, if you wanted to switch these around, reverse the order and put an f of x minus y in here, or I guess y minus, it doesn't matter whether it's x minus y or y minus x, right? Because it's going to be squared. In here it would. But I'm leaving it like this because we actually had this problem a couple lectures ago when I first showed you how to solve PDEs on unbounded domains. We had this exact problem. I think I called this h of x though, but it doesn't matter. We got the same solution, and maybe you remember that this involved the bell curve. We called it the heat kernel, and I'll leave it up to you as to which method you like best. I think I like the Fourier transform because you may remember when we first solved these, we did a little trick. I think I did something, I made an argument involving dimensionless quantities, and I did a sneaky little change of variables, which out of the blue maybe seemed a little bit arbitrary. So I think this is maybe a little bit more down to earth and more direct, but hopefully you appreciate that we got the same answer two very different ways. And that is a great place to stop. See you next time.